Good morning, Capsuleers, and welcome to the third day of Fanfest 2023. If you've ever wanted to peek under the hood of Eve, now is your chance, as we are about to explore the building blocks of New Eden. Please give a very warm welcome to CCP Vertex.
Good morning, everyone. It is so good to see you all. My name is Ben, also known as CCP Vertex, and I'm the development director of our core technology group known as Platform. I've been around Eve since the early beta in 2002, so this is actually my 13th Fanfest overall. It's really good to see so many familiar faces and friends. Having been around for the past 2 decades means that I've had the privilege of witnessing the evolution of Eve over the 20 years, and how we're constantly tweaking and improving things, modernizing the game, the look and the feel. Crafting the best visceral experience is something we put a lot of effort into. We take a lot of pride in that, because we want you to have the most visceral experience possible, the most immersive experience possible. And the last 2 decades, we've come a very long way in that journey. From Eve in the early alpha, all the way back in 2001, where the look and feel wasn't well defined at that point, to the open and closed beta periods of 2002, we're constantly evolving that look and feel. Modernizing the engine capabilities, the art pipelines, we've released countless 3D model redesigns, texture and shader updates, completely overhauling the lighting and visual effects, to the graphics API upgrades, moving from DirectX 9 to 11, and now we're on 12. This transformation represents 2 decades worth of modernization effort, all while needing to support your record-setting fleet fights, some of the largest PvP battles in gaming history, something you should be so proud of. You don't make it easy for us, but we really wouldn't have it any other way, and we are definitely not done with modernizing the look and feel of Eve.
CCP Games presents Carbon, a next-generation game engine. Pushing the boundaries of large-scale MMO technology to create entire universes. Forged over 2 decades, Carbon powers the Eve universe, creating worlds without limits. All you need to do is lose yourself in them.
We are proud to present Carbon, EVE Online's next-generation game engine, building on our 20-year legacy of breathtaking visuals. Carbon represents our vision of a modern game engine, supporting the latest in rendering techniques and features within an efficient and flexible framework. This effort extends to our tools and our pipelines so that we can increase our developer velocity, which means we can get features to you quicker than ever. Carbon will release with upscaling that best suits your choice of GPU vendor. So going off of our DirectX 12 and Metalwork, we will be supporting ray trace shadows and reflections. To complete that visceral experience, we will be adding support for 3D audio. And to ensure that the engine performs better than ever, we will have an all-new GPU-driven pipeline, which you will hear more about later in this presentation. Releasing early next year, Carbon enables new visual experiences for decades to come, ensuring Eve continues to be the ultimate science fiction experience. And now, I would like to hand over to our technical director, CCP Tuxford, to deep dive into the technology that drives all of these changes. Thank you.
Thank you, Vertex. I'm CCP Tuxford, and I'm Technical Director of Platform. Like Vertex, I've been here at CCP for many years in various roles, including game designer, software engineer, and technical director of Eve. And I'm here to talk about our physics engine, Destiny. So that is all messed up. Sorry about that. Right. There we are, little technical difficulties. So what is a physics engine? So a physics engine is a software component that simulates physical interaction in a virtual environment. It calculates how objects move, collide, and react to forces. In Eve, we have a proprietary physics engine called Destiny. It's simple and efficient. And it's a key factor that enables us to have these large fleet fights. But how does it actually work? The server runs a simulation for the entire solar system. But the client runs one as well for all items in local proximity. Basically, anything you can see, the client is simulating as well. The client will send instructions to the server, instructions such as orbit, approach, or line. Basically, anything you can see in the UI, all the interactions you can do. The client sends that to the server. The server will send that straight back to all the clients that need to know about it. And then everybody will progress to the next frame. Now, technically, the server doesn't really wait for the clients to progress to the next frame, but they all kind of do it in sync. This implies a few things. And the first thing is, we only communicate changes. You will get the initial state of the universe, but after that, you only get sent changes. This means that if there are no changes in the simulation, there's no actual network activity going on. And this is because Destiny is deterministic. If you don't know what determinism is, it basically means given the same input, it will yield exactly the same results. And because we're working on diffs, the calculations really have to be deterministic. Because any discrepancy may, for example, cause collisions on some simulations, but not the others. And those discrepancies will only grow as time passes. You may have already experienced this as desync. Sometimes it's because the client is actually missing some messages, but sometimes it's discrepancy in the calculations. Now, we haven't had one in a while now, but you may have already experienced the ramifications of it. So the third thing is the client needs to know pretty much everything that it can see. Because in order to simulate the state, we need to know everything. So I have a small example of this. Let's say we're simulating this raven. We just want to simulate where this raven is going. In order to do that, we need to know what its original position is, its velocity, and what it's actually doing. In this case, it is approaching that tempest. So we need to know its state, its position, velocity, what it's doing. It's orbiting the tempest, and so on and so forth. We also need to know about anything these ships can collide with. Collisions are an important part of any physics simulations. Collisions in Destiny are pretty simple, but more importantly, they're really easy to calculate. And this is because the geometry of the objects is pretty simple. All moving items are simulated as spheres, and finding collisions between two spheres is really, really simple. You just compare the distance between the centers to the radius of the spheres. And this is kind of fine for smaller ships. For stations and larger structures, it's very noticeable that they aren't spheres, especially when you start maneuvering your smaller ships around them. We have a pretty innovative solution to that. We just add more spheres to it. And since the structure doesn't move, the calculations are pretty simple. Some ships are also pretty big, and they don't have spherical geometry. They have spherical geometry, but they don't look remotely spherical, regardless of what we try to tell the artists. So, where are we now? Destiny has served us for 20 years, and we will continue to develop it and work on it. So in order to prepare it for the third decade of EVE Online, I'm going to tell you about some of the modernizations efforts we've been doing. The tick is really where all the magic happens in the simulation. We have an evolve step. That's where we move all the objects around and resolve all the collisions. Then we have everything that happens before the tick and everything that happens after the tick. This is pretty much what programming is about. It's like 3 lines of code. Do the thing before the thing, do the thing after the thing. Pretty simple. These are really poorly named things, do pre-tick, do post-tick. What really happens there in the pre-tick is we gather up all the messages we need to send to the client. All these approaches, orbits, and aligns that the clients told us they wanted to do, we gather them, send them to the relevant clients. So let's take a look at what happens in the pre-tick. So it gets quite complex, and it's a lot more complex than what you would reasonably expect for what it's doing. So what you're seeing here is around 20 years of gameplay logic getting intermixed with the physics logic. This goes on. There was a limited amount of time I wanted to spend in PowerPoint making this animation, but it's like 1,000 lines long. Why is this bad? So this is bad because whenever you make changes to this physics simulation code, it can cause unexpected failures in different systems. And this will cause you to lose confidence in making changes. And pretty soon you don't want to make any changes at all. And if you are making changes, you definitely do not want to make any big changes. This drives poor code because you shy away from making the structural changes to the code that are required. And then this causes unexpected failures again. So how did it really get like this? How did we make it like this? Reality is physics engine has been stable. There hasn't been a growing need to make any changes to it. So the changes being made have been catered to other systems. And that allowed it to grow around it. This is really common in software. It's just part of the entropy of being a software developer. And it's not particularly bad. It just means that before we start making any bigger changes to the engine, we need to do some maintenance work. As a starting point, we've separated the gameplay logic from the logic that prepares and sends the messages to kind of encapsulate Destiny and make it detangled from the rest of the code. And by simplifying and decoupling our physics engine from gameplay, we've opened the door to creating targeted benchmarks. And this allows us to precisely measure and enables us to improve Destiny's performance. Because if you can measure it, you can improve it. So all of these changes were made to give us confidence, the confidence to change Destiny. But what kind of changes are we really talking about? Destiny is efficient, but there's still plenty of room for improvement. One of the most resource-intensive code in our cluster, in a fleet fight, is sending the Destiny updates to the clients. Let's take a look at what happens there. So Destiny runs on both server and client. There's a server side called Beyoncé. It gathers the instructions, all these approaches, orbits, aligns, and everything, explosions that happen, and sends them to a client-side service called Michelle. These are definitely Destiny's Child references, by the way. And it gets those to the client-side Destiny. The Destiny code is all written in C++, but the services Beyoncé and Michelle are written in Python. And if you know nothing about programming, then C++ is really, really fast. Python is kind of slow. There are top people working on that, but that's the reality of the situation. The logic for determining which, this means that the logic for determining what messages to send to which client, along with the marshalling, unmarshalling, and the data transmission, is all handled in the slower Python layer. And if you're unsure about what marshalling and unmarshalling is, you can imagine marshalling as boarding a plane, data transmission as the flight, and unmarshalling as the onboarding. By separating the gameplay logic from the physics logic, we're in a pretty good position to send all Destiny packets within the C++ layer. This is because all the information we have is really inside Destiny. It's difficult to say what the net effect on performance is, because there's a lot of other things happening other than physics simulation. But for all the code, we've seen the efficiency of the data transmission go up by 2 orders of magnitude. The other side of performance is fidelity. And by that, I mean how realistic the simulation feels. It's clear to us that representing ships as sphere does not fit all scenarios. We use different shapes and even multiple shapes to represent static objects. Could we not use those for ships as well? We could, but at what cost to performance? With investment in modernization such as Benchmark and more test automation, we can know exactly what that cost is. So for 20 years, Destiny has been a reliable foundation when it comes to physics. Our recent code modernization sets us up to boost performance and fidelity. But what about other kind of more game-changing improvements? Now, quick caveat before I say that, the upcoming feature is purely hypothetical. It would need design validation, which has not happened at all. Think of it more as what could be, not what will be. Imagine being trapped in an asteroid field, surrounded by hostile ships. Outgunned, but not outsmarted, you spot a nearby cluster of large asteroids. You dart toward it, evading incoming fire. As you move behind the asteroid, the hostiles no longer have a clear line of sight, which causes them to lose their target lock on you. Seizing the chance, you line to a nearby planet, initiate warp. Just as the enemies regain the lock, you hear the sweet words, warp drive active. So now that you're up to speed a little bit on the server side, I would like to introduce Makio, who will talk about some of the updates to the client.
Hello, everyone. My name is Daniel, also not really known as CCP Makio just yet. This is actually my first Fanfest. Thank you. I am a rendering engineer on the engine team, and I'm here today to present a little bit about some of the rendering work that we've been doing. And to start that off, I want to introduce you guys to Trinity. EVE Online is a very unique game, not just for you players, but also for us engineers working on the rendering. We have a very large world. We have a very high view distance in this world, and there's a large number of things to render. It's also massively multiplayer online, which means that we have no real control about what you, the players, do in the world, so we need to be prepared for anything. Trinity is the graphics engine inside of Carbon, and it's our solution to graphics. So some of the visual improvements that we've been working on lately. I'm sure you're familiar with the improvements to shadows. We now have an unlimited number of shadow casters and shadow receivers. And the shadows overall are just much, much sharper than they used to be. These shadow changes go hand in hand together with the new volumetric cloud effects that we have, which are obviously very prevalent in the new area that just unlocked yesterday. It's a really, really beautiful effect, and I would love to talk a little bit more about it. Unfortunately, we don't have time for everything. So I will move on to probably why you're here, which is the new stuff. Ray tracing. So what is ray tracing? Well, it's a hardware feature of your graphics card that allows you to shoot rays arbitrarily in the scene and see what they hit. We're working on support for both Windows and Mac. And the cool thing about ray tracing is that it enables us to do a bunch of new techniques that we simply weren't able to do before. This includes stuff like improving the reflections and improving the shadows even more, as well as hopefully improving the lighting overall in the future. The cool thing about EVE Online is that space is fairly empty. So you can count on ray tracing not having the same kind of performance hit that you're used to seeing when enabling it in other games. So looking a little bit at the ray traced shadows, Well, we already have shadows, of course, but ray tracing allows us to simulate the size of the light source in a much more accurate way. If we add a shadow caster to this little scene here, you can see that only some of the rays will be blocked, and the actual shadow that you see from this very large light source will be very soft and diffuse. Yeah, this is fully realistic and fully dynamic, which means that if you have for example, an antenna sticking out of your ship, it will cast a perfectly sharp shadow onto your own ship, while the distant space station will cast this very, very soft shadow on your ship, and these two kinds of shadows will seamlessly mix. We have a prototype working, as you can see, but it's still very much work in progress. We also really want to improve the reflections. We, of course, already have support for limited reflections, but ray tracing will truly help us take them to the next level. You can imagine the metal parts of your ships reflecting the dynamic environment around you in a way you haven't been able to see before, as well as, or for example, seeing a perfect mirror-like reflection of your ship as you pass by a frozen asteroid. No prototype here just yet, but it's something we're very excited about. But of course, graphical improvements aren't everything. We also need to make sure that it all performs well. We do always try to optimize our code and our shaders, stuff like that, but there is an upper limit to how far you can go with just minor code changes. Sometimes we need to take just a completely different approach to rendering something to make sure that we maintain the performance. And one of the biggest challenges there is just pixels. It's just the sheer number of pixels that we need to render. The number of pixels is, of course, determined by the resolution of your monitor. 1080p monitor is about 2 million pixels. 4K bumps that up to 8 million. And that's the number of pixels we need to render every single frame. Of course, the cost of each pixel will also keep going up. We are always adding new shading improvements, such as the shadows. We're adding new special effects and post-processing effects to make sure that the game looks as good as it ever can. And on top of that, we want to add ray tracing. And all of these increase the amount of time we need to spend on each pixel. And we can't forget about anti-aliasing. Anti-aliasing usually comes in the form of some kind of resolution increase. Again, increasing the effective number of pixels we need to render. So it kind of multiplies the cost yet again. And obviously, the solution isn't to just get everyone to get a really expensive GPU. Would be nice, but that's not the reality we live in. But then looking into anti-aliasing specifically. Well, what is aliasing and why are we trying to get rid of it? Well, aliasing is essentially an artifact of the way that GPUs render triangles and things in general. You basically have this binary test for each pixel that checks if the center of the pixel is covered by the triangle. And if it is, it's completely filled in. And the end result is the image to the left here, where you can see these ugly jagged edges, this kind of staircase pattern. It's very typical of aliasing. And anti-aliasing is essentially any kind of method that attempts to generate the image to the right, which is something that just represents the actual physical shape of this triangle much more accurately. But aliasing doesn't just happen at the edge of triangles. It can also happen in the middle of triangles, such as in the case of these specular highlights. So what's happening here is that the highlights on this hull here they are very, very thin, and therefore it's essentially completely random if just a row of pixel centers happens to kind of randomly end up on this reflection. And when they do, they pop into existence and then briefly disappear again whenever the camera moves. So it's essentially a problem of details that are smaller than a pixel that we can't capture with this. One of the most naive and simplest approaches to anti-aliasing is supersampling. It's a very simple idea. Instead of doing a single sample at the center of each pixel, we simply do multiple samples. It's effectively the same as just rendering at a higher resolution. Then at the end, we kind of just average together all of the samples inside of a pixel, which again is effectively the same as just scaling the image down again. This is really, really effective, but it also is really expensive. If we're doing 4 samples for each pixel, for example, that's 4 times the amount of shading work and lighting, so all that good stuff. On top of that, we need 4 times the amount of memory to store all these samples, and we also need 4 times the amount of bandwidth to read and write these samples. So 1080p effectively becomes 4K, 4K effectively becomes 8K. Everything becomes so much worse. But it is really, really effective. You can see the comparison here. To the left, we have no anti-aliasing, and to the right, we have 4 times supersampling. As you can see, all of this ugly shimmering and all this distracting shimmering is completely gone. It looks absolutely amazing. Unfortunately, because it's so expensive, Eve has so far been forced to rely on something called multi-sampling. So multi-sampling is an optimization of supersampling that essentially only tries to supersample the triangle edges. So we're still only shading once per pixel, but we actually choose which samples to actually write to. And we write the same color to all of the samples that are covered by the triangle. You still need to pay for the memory and the bandwidth cost, but the shading cost increase is essentially negligible, and that's where the bulk of the cost comes. The big drawback of this is, of course, there's no anti-aliasing for the shading in that case. So if we again look at this shimmering image here, the only thing that multi-sampling really fixes is that top jagged edge, like that staircase pattern on the edge of the hull there. You're not going to see any kind of impact at all on the shimmering inside of triangles. It would be really, really nice if we could afford supersampling, but we can't. But what if we still do one sample per pixel, but we kind of start moving it around inside of the pixel, so we do a different center every frame, and then we kind of just add them all up at the end. Well, that's the foundational idea behind temporal anti-aliasing. The idea is basically that you spread these samples out over time. You do one sample per pixel, but a different sample every frame. The idea then is to blend it all together really carefully to get the effective result of 4 times supersampling. It's really effective, and it's actually even faster than 4 times supersampling. 4 times multi-sampling, simply because we only need one sample per pixel, just like when we have no anti-aliasing at all. But you do need to be really, really careful when doing this. If you end up blending when you're not supposed to, you can get blurriness, you can get ghosting, where you can see parts of the previous frame. Looks very terrible. And in fact, if you blend too little, you also get problems. You can't just disable the blending completely, because then you will suddenly start to be able to see this kind of jittering motion around as you move where the pixel center occurs. And to take an actual visual example of this, here's a very zoomed image of an hangar. You can see that it's very pixelated, and you can also see that it has these ugly staircase patterns everywhere. This looks even worse in motion, where you will have a lot of shimmering effects as this moves. So when we apply temporal anti-aliasing, we will first start to sharpen the image as much as we can, and then start kind of moving it around a little bit. And all of these images are slightly different, so when we add them all together, we end up with this really, really nice and smooth result. We still have all of the sharpness of the texture detail, all of that good stuff, but we have managed to eliminate the staircase patterns, and on top of that, it's much, much more stable in their motion. Looks very, very good. But can we actually take this approach even further? And it turns out that we can. It's called temporal upscaling. The idea is to start at an even lower resolution. We don't actually start at the full resolution. You can imagine moving this single sample that we have around in a 2x2 area instead, so over 4 pixels instead. We then temporally upscale this beyond the full resolution to again get this kind of super sampling effect, and then scale it back down to full resolution, well, what your monitor has. And this works. It works really well, but it is even more challenging. Any kind of issues that you would normally have with temporal anti-aliasing, such as flickering or blurriness or ghosting, just becomes so much more obvious when you're kind of blowing it up to twice the size, basically. Fortunately, this isn't a problem that we really have to solve ourselves. There are numerous temporal upscaling, or at least temporal upscaling functions, algorithms that already exist. And we are planning on supporting pretty much all of them so that you can pick the best solution for your specific graphics card. We will be supporting AMD FSR 3. We will be supporting NVIDIA DLSS 3.5, Intel's XeSS, as well as Metal FX upscaling on Mac. So that kind of makes sure that even as we're adding all of these new features, even on weaker graphics cards, you will be able to enable these new goodies with a minimal loss in image quality from the upscaling. But your GPU isn't the only thing that's kind of struggling. What about the CPU? Well, the GPU and the CPU have a very interesting relationship. They're essentially 2 completely separate processors that coexist inside of your computer. And it kind of works the way that the CPU sends commands to the GPU and tells it what to do. And in some cases, we can actually end up with a case where the CPU simply doesn't have the time to generate enough commands for the GPU. And the GPU will just sit idle and not have anything to do. And that's where our GPU-driven pipeline project comes into play. It's quite a bit of a complex topic, so we will need to take a deep dive into how this relationship between the CPU and the GPU work. So to understand this, let's have a look at a timeline where we can see what the CPU and the GPU are up to at any given time when rendering a frame. So the CPU is, of course, responsible for a lot of different things. It's not just responsible for graphics. Things like physics, networking, network code, as well as the user interface, all this kind of good stuff and a lot of other things. This is a bit outside of my area. I work with the graphics, so I'm just going to group all of these up into this big block and call it gameplay. But at some point, the Carbon engine will have processed all of the other subsystems, and it's now time to start rendering something. And at that point, it will gather up a bunch of commands, and it will kind of send them off to the GPU. And the GPU will then start processing this and rendering that frame. But the CPU doesn't just sit idle as it waits for this to complete. No, it will immediately move on to the next frame, and the frame after that once that's done. And in this case, this works really, really well. The CPU even has a little bit of breathing time, and the GPU is taxed to its full capacity. It's working 100% of the time. But there are cases in Eve, quite a few cases, where this is not the case, where this submitting of the gathering up all of these commands and submitting them to the GPU actually takes longer than it takes for the GPU to render them. And this can happen simply because of massive fleet battles or a huge amount of detail, and it also depends on your specific hardware, like the relative power of your CPU and the GPU. And in this case, well, we're wasting a lot of time on the GPU. The GPU is essentially sitting idle for a very large amount of time. And we could, in theory, push the GPU to render maybe twice as many frames per second in this case. But to understand why this happens, we need to look into what actually happens in this submit block to make it so expensive. And to do that, we need to figure out how we're rendering a single specific, like a single Eve ship, like a single ship in the universe of Eve. So I present to you an Eve ship. I promise. This is definitely a ship. Like a real Eve ship, it has a mesh, which is determined by the shape here. It also has a shader, which is determined by the color here. And it also has a material, which is represented by the texture applied to this. So to render this ship, we actually need to submit 4 separate commands to the GPU. We need to set which color we want to render it with. We need to set the shape that we want to render. And then we need to set the texture. And once those are done, we can submit what's called a draw call, which is essentially a command that says, yeah, draw something using the previously set stuff. And if we were only rendering one ship, this would not be a problem whatsoever. This is just 4 commands. Problem is, Eve has a lot of ships. Some might even say dozens at times. So we need to really be able to render this many things. And well, the first thing we're going to do, I'm a programmer at least. I love lists. I'm going to move them all into a list. This will make it much easier to work with. And once they're all in a list, well, it isn't that difficult to just kind of do a naive loop over this and render them. We'll just go through all of the ships that we have to render. We'll set the color, we'll set the shape, we'll set the texture, and issue a draw call. There's actually 100 ships in this image, or in this scene. So we will end up with a total of 4 times 100 commands, which is 400. Very simple. However, this is not the most efficient way of doing this. We are actually switching between the same colors multiple times, for example. So we can actually eliminate a bunch of commands by kind of just reorganizing this data. So if we move this down here, and then we make new lists, we make one list for each color. And then we kind of just take all of these ships, we go through them, and we sort them into the color. We sort them based on the color that they have and put them in the corresponding list. Well, it turns out that we can render these lists much more efficiently now. We no longer need to switch the color for every ship. We can just set the color once and then render all of the ships that use that color. And the end result is that we eliminate almost 25% of our commands. And we can actually take this one step further. We can start sorting things based on what shape they're using as well. And that will allow us to eliminate even more draw calls. In fact, we no longer need to change the shape as often now. So even though we're rendering the exact same pixels on the screen, the exact same triangles, we are now doing it with almost we are now doing it with almost half the draw calls of what we were doing before. And this process of kind of just reorganizing the data to render it more efficiently is called batching, and it's a very important thing. So yeah, problem solved, right? Let's see what happens with our timeline. Well, our submit block is now really, really tiny. The problem is that now we have a batching block instead. And that it turns out that just reshuffling all of this data and taking care of it is really expensive as well. What if we just kind of take this original list of ships? We just yeet it directly at the GPU with no regards for its safety. We just don't care. And we kind of just let it figure it all out for itself. That is what the GPU-driven pipeline is all about. So it turns out that GPUs nowadays are really, really flexible. They can actually generate commands for themselves. They don't need a CPU to tell them what to do anymore. So we can actually have the GPU do this batching for us. And the best part of this, well, one of the good parts at least, is that it's even faster than the CPU at doing it. The actual best part is that there's minimal CPU involvement. The CPU is now free to do other things while the GPU keeps itself busy. So if we look at our rendering loop that we had before, we can kind of eliminate everything inside of that loop there and basically just set the color and then tell the GPU to do its thing. And we eliminate more than 90% of the CPU side draw calls and commands that need to be sent there, while the GPU still gets to execute all of those 200 plus draw calls that we had before. But it's fine, because the GPU was already not being taxed to its full capacity. So that's all good. And what happens to our timeline? Well, we used to have this batching block that was on the CPU timeline that just magically moves down to the GPU's timeline. And in fact, the batching block is actually significantly smaller than this. This is just the smallest block I could get in that could still fit the word batching. So what does this ultimately mean for Eve? Well, it's a complete restructuring of how things are rendered inside of Trinity. It's a lot of work. There's essentially no shader that's going to come out unscathed by these changes. It's a lot of work, but once it's done, we are confident that we will be able to have a lot more objects on screen, and we can really let our artists go crazy with this. And also more variation inside of those objects. We no longer need to have copies of the same objects to make sure that it works well with batching or something like that. We can just have more unique objects and let the artists just get more free hands. But the best part about this is just that it frees up the CPU for game logic. It means that the entire graphics engine just kind of moves out of the way of all the other systems that also require the CPU time, which will, for example, enable for the new physics improvements that CCP Tuxford was talking about before. But then the big question is when? And, well, CCP Verdict's already spoiled this. Early 2024. We want to get all of these improvements, including the upscaling, the ray tracing, as well as the GPU-driven pipeline done in early 2024. That leads me to my final question. How do artists actually work with all of this new stuff that we're giving them? And that's where I hand over to CCP Amino.
Thank you. Oh, hello. So, my name's CCP Amino. I'm a tools developer with CCP. And so our job is to try and take the power that Carbon brings to our game and put it in a package that will allow our artists and designers to leverage that to build great experiences for you. So with the big investment in Carbon, we've also been making a big investment in these tools. And I would like to introduce you to our new, very internal-only tool, Graphite. So Graphite is a sort of editor for everything you might want to do in the engine. Whether you're making a new ship, skinning an old one, building a whole new scene for you guys to explore in New Eden, or even badly trying to make a trailer like I am here. You can basically use it to leverage the power of Carbon in order to build all of the experiences that we want to deliver to you in the game. And we've been working on this for quite a while. We've actually started from the ground up with the UI here. We've been trying to modernize our tools internally overall, try and bring all of the capabilities of Carbon together under one tool set, and empower our artists and designers to deliver bigger and bolder experiences leveraging all of the new benefits with the new engine. Some of the improvements we were making are actually just really simple. In some cases, it's just about taking a system we already have, fitting a turret to a ship and shooting another one, making it explode, making that feel a little bit more in our tool set like it does in the game. The important part here is having artists being able to use this like you're going to experience it will allow them to hopefully build a higher quality version of that turret, something that feels better to use, is more fun to play with, and they'll be able to get that experience a lot earlier in their development cycle. In some cases, it's about bringing tools home. When it comes to doing things like defining collision geometry, we've historically leveraged third-party tools, have artists work in there, build the kind of data that we need for Carbon to consume in order to do the collision work. And that's quite a long-winded pipeline. The artist will spend a lot of time in this third-party tool, be it Maya or Blender, try and author this data, and then they've got to go through the process of getting it into the engine to see if it works, to see if it plays nicely, to see if they've introduced some really weird bug where you get stuck in the middle of a station. So by bringing these things all under one roof and bringing them home, we plan to leverage this to deliver higher quality to you in the game experience. In some cases, we're actually looking to improve our developers' experience as well. Many of the places they'll spend a lot of time is doing things like crafting a beautiful scene for you to explore. They want to visually tell a story, use their art assets, and show them off to build big, cool things for you to discover and enjoy. And we want them to spend more of their time expressing themselves and designing what they want to deliver at the end, rather than spending time fighting against the engine and the tools that they have at their fingertips. So we put a lot of time and effort into leveraging some of the performance benefits that come with Carbon to give them a much nicer overall experience, smoother, prettier UI, make it a little bit more functional, make it a little bit more adaptive, make it feel good. If it's a pleasure for them to work with, then hopefully they will deliver something very pleasurable for you in the end. In some cases, we are actually trying to make use of and leverage the power of some third-party tools. You'll have seen a lot of the new cloud tech being used. This technology is authored by artists in something called EmberGen. And that tool will spit out data that Carbon can consume and we can put in the game. Before we can actually get it into the game, there's a lot of other little things that go into a little bit of overhead. And ultimately, they end up working heavily in isolation inside of a toolset outside of our ecosystem, crafting those clouds. So what we're trying to do here with Graphite is make sure that they have as smooth and as fast a pipeline. So when they're using these third-party tools to build big new clouds, we are very quickly getting them into the engine. In this case, preferably almost instantly. They make a change in EmberGen, and we want them to instantly see that in Graphite. But along with that, by having all of our tools under one place, having the tools that they use to author scenes, this allows them to see not only their cloud very quickly in Engine and see what that's going to look like, but see it in the kind of place that they're going to use it, allowing them to craft more bespoke assets that fit the scene and better tell the story or better describe the experience that they want to give you. In some cases, we're leveraging whole new capabilities. So Carbon brings a lot of benefits in terms of new performance, better options, and this provides new opportunities for designers and artists to take advantage of. Every time we save a couple of frames in the engine, maybe that means explosions can be bigger. Maybe that means scenes can be more complex. There's less restrictions on the work that they do. And so this is quite an experimental feature for us, but we're trying to leverage the power of third-party tools, in this case Blender, again with a really direct pipeline. So the artist can work in Blender and craft very large assets, hit one button and see it very quickly ported straight into the game, try it out. How does it feel to fly around? How does it feel to bump into it? How does it look? And by giving them this pipeline, the plan is to allow them, again, very early and very experimental, allow them the power to build much bigger and grander experiences overall and deliver to you the best possible experience that they can manage to make Eve awesome forever. Thank you very much. So if you have any questions, you'll find many of us around. We're all very friendly. Come and say hi, have a chat. We'll happily talk your ear off for hours about all of this stuff. But we also have a panel on the second floor. So if you're in the mood, we'd love to see you there at 1:30. Thank you.